As we already discussed, I'm going to present, or we are going to present LibAFL, the advanced fuzzer library. We, that's me, Dominik Maier, and Andrea Fioraldi. Both of us are, hi. Both of us are academics, so we're doing our PhDs at TU Berlin, Euricom. We're both participating in CTF context actively, and we're both part of the afl-fuzz team. Some in the fuzzing community may know afl-fuzz as a large community-backed fork of AFL. And over a year ago, we started creating a library with the lessons learned from afl-fuzz. We call LibAFL for Advanced Fuzzing Library this time. It's not written in C, it's written in Rust from scratch. And we're gonna go in depth in this talk. We will present the library. Specifically, this is a coding session, so we will see a lot of code, how to build a simple harness. And the lab, why would you want to watch this talk at all? Because it's a very fast library. It's a way to build very fast fuzzers with low IPC and runtime overhead. The fuzzers are scalable, almost linearly. They are portable, so we used it to fuzz Android, we fuzzed on Windows, we fuzz on macOS, we fuzz on Linux, and we even are able to run this, for example, inside ITA with no standard lib from Rust side. We support state-of-the-art contexts like fuzzing, hybrid fuzzing using SimCC or grammar fuzzing, and just the normal AFL feedback fuzzing as well. And it can run on multiple instrumentation backends. So we have a binary-only backend using Frida for Windows and macOS. You can also use QEMU on Linux. And there's, of course, source-based instrumentation, for example, using Clang. And you can even use it to instrument other languages that are not compiled. We have an example that uses Google's Atheris for Python. And most importantly, it's very extendable with your own components. So we built this in mind with the researcher that wants to build their own new concepts. And we will show how to use the library to build your own fuzzer with a very simple example that I'm going to present, and then with a more advanced example in code by Andrea. If you are rewatching this talk at home, or if you just want to get into it, see the fuzzers example directory inside the repo, see our book, or the API docs of Rust to get started. Why even have this library? Well, we saw that there is a lot of different fuzzers around, all of which are kind of related. So you see in the middle here that there's AFL, and then there's lots of forked off or rewritten fuzzers. All of them are designed to be its own little tools, and none of them, or none that we know of, are designed with code reuse in mind. So that makes them pretty hard to extend. This also makes every single fuzzer that you've just seen in the other image to be incompatible forks of each other. So you can't really use a technique that's completely orthogonal to another technique in the same fuzzer without a lot of copy pasting code around. So obviously the solution is to have like an abstract idea of fuzzing concepts and make them pluggable. We presented the whole idea already at RC3 last year, where we explained how a fuzzer can be thought of as different Lego components. And in this talk, we're going to go into the code, how to actually use this library. So first of all, I'm going to show you how to build a simple fuzzer step by step and explain it along the way. The one thing that every fuzzer usually has is some kind of target. So in our case, this is a simple function. And this simple function, this is Rust. The whole library is in Rust, but obviously you can also fuzz C, C++, other things. But for now, you will have to get used to Rust for this talk. I'm sorry. But you can trust me that this function just takes an input and then checks if it's ABC. And if the input is ABC, it crashes the program. So that's all this does. And in the simple example, we will first of all generate a random input. And let's see how we do this. First of all, we need a state. Every fuzzer in libafl has a state. A state evolves over time and can be serialized to disk. And that way we can restart the fuzzer at any time without any issues. And we need stats, a status screen that shows how the fuzzer is progressing. We have a very simple stat that just prints each line. You could eventually also get into more crazy stats and show like a real AFL output screen. Then we have an event manager, and the event manager gets events like, oh, there's a new test case, and then does things with it. Like in a more advanced scenario that Andrea is going to discuss later, it can forward the event to other nodes in a fuzzer cluster. Then we have a scheduler that just schedules which test case should be used next. And then we have a fuzzer, which is like this backbone concept that keeps this all together. And then we have the executor. An executor is something that does anything with the target. In the in-process executor just calls the target, checks if it crashes, and if it crashes, just reports back the crash. But we also have, for example, a fork server executor that would do the normal old school AFL style IPC to a target. And then we generate the input using a generator. We have multiple generators, for example, a printable character or printable generator. If you use this, you will just have a byte array of random input with each time you call this generator. And then we use state.generate initial inputs to generate, in the 8 in this case, initial inputs for the fuzzer. Right. So building this, we see here in the last line, loaded 0 of 8 initial test cases. The 0 means that there was no feedback that thought, oh, something is interesting. And we just have 8 initial test cases that we generated using the generator. Yeah, so what we did so far, we created a state. We are able to print stats. We created a simple event manager and an executor, and we generated some inputs. Right, this is already kind of fuzzing, but it's basically piping def u random to the target. It's not super interesting. Modern fuzzers use feedback. So a modern fuzzer usually observes the target and learns if there's something interesting going on in the target. And then that way it can see that one of the inputs is more interesting and it can focus on this interesting more. While most fuzzers instrument the target to get coverage as a metric, for this simple fuzzer, we don't instrument the target, we build the instrumentation ourselves. So we just add to the test case that we saw earlier, we just manually add like a kind of branch coverage. So you see here, each time we pass an if condition, we increase one element in the signals map. And that way the fuzzer will see, oh, we found a new branch. This is what usually you do during compilation, but we just do it manually here. Then we get the signals map and pass it into a map observer. Observers are a concept in libafl where you can observe the target. So there are multiple observers, like a time observer or a map observer. In this case, we're using the map observer. And then we pass the observer to the executor, so the executor knows about the observer and uses it. And then we need a feedback. A feedback then takes the observer, looks at the observer, and decides for each single input run if the input was interesting or not. So there's basically a thumbs up, thumbs down. And in this case, we're using the max map feedback, which tries to maximize each value in a map. This is roughly what AFL also would do with its coverage map. And on top, we use a crash feedback, and the crash feedback would give a feedback about the target if it crashed or not. Then we put this all into the state. So we create two corpora, one being the in-memory corpus, which is just doing fuzzing. So each new test case that is interesting from one of the normal feedbacks is put into the normal in-memory corpus. And then we have a second corpus that finds all the solutions. So there's basically a crash is a solution. and that gets put into the sec corpus. We could also put, for example, each timeout there, or we could also even put every single new path there, but obviously that would be useless. It's just the solutions are no longer used during fuzzing. They're just the solutions from a conceptual point of view. Well, then we create the fuzzer. And yeah, to recap, we use a map observer and a map max feedback. And then we use the crash feedback to see if it's something crashed. We put all of this in corpora. The observers and feedbacks in libAFL are decoupled, so we can use the same feedback for another observer, or we can even use feedbacks that span multiple observers. Right, so now we created input, now we have some feedback. Now let's get to the actual fuzzing. What do you need to do? We have the feedback, and now we want to mutate it. So what we do is we create a mutational stage. There are multiple stages in libAFL related to different concepts. One of them is mutational fuzzing. The mutational stage, the standard mutational stage, just calls different mutators in a row on the test case that is passed to it. And then we'll do that for each test case, and the scheduler will schedule new test cases in. Then we just call the fuzz loop, and the fuzzing starts. And yeah, let's see. If we cargo run this in release mode, we see different log outputs, and we see that we never even calculated an executions per second because this function is so small and the mutators are so effective that we just basically crash immediately. And since this is a very simple example, we don't restart afterwards. For this, we need a more advanced setup that Andrea is going to talk about now. So handing over to Andrea. Thank you.
Thank you, Dominik, and hi to all. I'm going now to build with you a more complex fuzzer using QEMU. Why QEMU? Because it's a recent addition to LibAFL that it has less than a month. So maybe you followed LibAFL before, played with other instrumentation engines, and so maybe even if you followed LibAFL before, this talk will be useful for you to discover a new feature. What is, in brief, QEMU? QEMU is an emulator that has a full system and user mode. We are going to use the user mode to emulate just a process in the user space in Linux. It is based on dynamic binary translation. So the code is translated into an intermediate language and recompiled. So you can run a code for another architecture on your computer. And we extended QEMU to expose an API that allow the user in Rust to completely control the emulator and set hooks for interesting situation like report each time that we execute each basic block or each time that we access a memory address and so on, and to control the guest state, so writing memory, reading registers, mapping memory, and so on. You can load ELF on Linux with our library based on QEMU, and fuzz with coverage, snapshots, and many other juicy features with binary-only fuzzing. In our library, the first step is to initialize QEMU. That is now a library, not anymore binary, like you are used to use it, with the arguments and the environments of the guest process that we want to emulate. And then for this example, I'm going to show you how to fuzz any binary with a libfuzzer harness that, as you know, the entry point for libfuzzer is LLVM fuzzer as one input. And in this setup code, we are going to resolve the symbol in the binary and put a breakpoint on the harness function. After running until the harness, we can use our API. So you can see reading registers, reading memory, and so on. The API is very simple. It's like any other emulator that you are used to, like, I don't know, Unicorn Engine and so on. But it's really fast because there is less overhead than Unicorn, for instance. we use the memory mapping of the native kernel. And here I'm going to read the return address of the harness, put a breakpoint on it, and map a memory area to put the test case that we generate at each iteration of the fuzzer. And here our new harness. Unlike the other that there is code, here I just use the emulator API to write the input that is the argument of the harness to the memory area that I mapped before. And then I restore the registers. Like I set as first parameter of the harness in the guest, of course, so LLVM test1 input, the address of the test case in memory, the length, and so on. And I run the emulator until the next breakpoint. That, as you remember, the next breakpoint is the return address. So in this way, I can loop over the harness in an indefinite way. Having that, now we can build a more complex setup for the fuzzer, unlike the one that Dominik showed us. We can use the launcher. The launcher is a facility in LibAFL that can be used to spawn multiple instances over cores and machines, because can be synchronized using TCP. And with the launcher, we have the facility to restart crashing instances. Because if we are fuzzing in memory, like we do with an emulator, if the fuzzer crashes, we have to start another process. So we set up an intermediate restarter that when the fuzzer crashes, serializing the state, spawn another process, give the previous state, and so the new process, even if it is completely new, can restart from what the old process was left without so much overhead, like in other fuzzer, executing again the entire corpus and other stuff. All these fuzzing instances are bridged to a broker for the communication, and they share the events. As you remember, we have the event manager. In this case, the event manager is based on LMP, that is a low-level message passing. That is a protocol that we designed using shared memory, so it's very fast, zero overhead, and each fuzzing instance can share messages without touching the kernel. So again, on our code, the launcher executes for each fuzzing instance that we want to spawn this callback run client that is taking a state as option. The option set to none means that we have to create the state. The option set to something seems that the launcher is giving to us the state from a previous instance that may be crashed. Here, the observers, as you can see, are a bit more complex because we are going to use the map, the edge coverage map provided by us by the QEMU library to report the edge coverage, and the time observer because we are interested for some other components that I will show to know for each execution the time that it's going to take. The feedbacks here, as you can see, you can build derivative feedbacks using Boolean expressions. In this case, they are in OR. For the normal feedback, we want to still here maximize the map for coverage, but we are going also to use the time feedback that report the execution time to the new test cases as metadata. And as objective here, we are not just interested to crash it, but we are interested in timeouts too. So here the state creation. So if the state option is empty, we create a new state with a normal corpus and the solution corpus, or we just unwrap the option that the launcher gave to us. And here are some bits from FL. If you remember, Dominik showed us a Q corpus scheduler before that was just saying, okay, each time that the fuzzer needs a test case, pick it from the queue in a first in, first out fashion. Here we are using a corpus minimizer based on the execution time. That's why we need to report it with a feedback and the length of that test case, just like FL is doing. And so we have these implemented pieces in our library you can use if you need a more complex solution or a different solution of a naive solution like before. And here the executor that is almost equal to the in-process executor that we saw before, but in this case, the QEMU executor has an additional field that we can set, the helpers. The helpers are just facilities that set hooks in the emulator. In this case, there is just one helper, the edge coverage helper, that set the hooks to report the edge coverage. In these hooks, we report the edge coverage to the map that we have seen before. And we are going to finish this fuzzer, implementing a way to load test cases from a directory. Before we were generating them from scratch. Here we are loading test cases from a directory and set up a mutator that is an FL-like or a bit level mutator like FL long fuzz and many others fuzzer that work on byte streams. But in the library, you have a lot of mutators that you can use. For instance, grammar-based mutators or even mutators that try to understand the structure of the input and do some calculation or to learn the input format and so on. And so the next step is naturally, now that the fuzzer is almost finished, to run it and see. And that's this fuzzer running over a binary that is basically just libpng with the harness from MOSFuzz. As you can see, we break it on the harness, and we spawned the fuzzer on 4 cores, and then the fuzzer starts fuzzing. This fuzzer has very little kernel load, almost nothing. Just when we find a solution, it is written to disk, because the target doesn't make so much kernel interaction apart printing a standard error, and the fuzzer is almost not using any syscall here. So thanks to the fast message passing on shared memory, we can reach on 80 cores even 10 million execution per second. So now, many users that maybe are not interested in writing their fuzzer, customizing every bit of their solution, may want to just have some high-level API to do that. On top of LibAFL, we have another crate that is called LibAFL Sugar that just implement default good-to-use fuzzer implemented using the API that I showed to you. These just few lines of Rust implement the entire fuzzer that I showed to you in a very simple way. You can just set input directories, output directories, like you do with the command line of afl-fuzz, and then specify an harness that is using the emulator APIs, like before. Now, many people I know that maybe are not familiar with Rust or want to just prototype quickly a fuzzer. So what we did is to extend our library to Python 2. At the moment, we just implemented bindings for the Sugar API, so the high-level ones. And you can build the very same fuzzer that I showed to you in Python. And in the future, we are planning to extend the bindings even to the low-level APIs so that you can customize every bit of your fuzzer. Of course, our library is a free and open source software. We already have in this year of activity some contributors with some attention of the community, and we had even 2 students in Google Summer of Code, and we are going to participate again the next year. So if you are a student, you can apply and work on nice cutting-edge research on fuzzing with us. There are already fuzzers based on a LibAFL, like TLS pathing you can find on GitHub. You can see the link on the slides. That is a master thesis, really nice, using our library. And there are even other reasons. Even if you don't want to use LibAFL as backbone for your fuzzer, a thing that I suggest you to do, but maybe you don't want, is you can just use LibAFL borrowing the mutators, or just use the operating system facilities that we built to run on many operating systems like Android. You can use the data structure that we built to allow extensibility in Rust, that is AnyMap, that make the state serializable with code reuse. Or you can just use LLMP to scale over course your communication, or just use the QEMU bindings for, I don't know, your reverse engineering tool. So, small recap, LibAFL is a library to build fuzzers, not a tool. We plan eventually to migrate FL++ to Rust using it in not a near future, by the way. There are example fuzzers in the library that outperform state-of-the-art fuzzer in scalability and execution speed. There are already modern and state-of-the-art algorithms implemented into it that you can use. It's open source, and we have a growing community, and if you like it, you can join it. From me and Dominik, that's all. Have a nice FuzzCon, and see you.